Hello everyone, we are Division T Group 12. We will be representing floating point representation. Moving toward the slide of contents, Introduction to floating point representation, IEEE Standard 75 for floating point numbers. First of all, single precision IEEE 75 for floating point standards. Second, double precision IEEE 75 for floating standards.
Let's start with the introduction to floating point representation. To convert the floating point into decimal, we have three elements in 32-bit floating point representation: sign, exponent, mantissa. Sign bit is the first bit of the binary representation. 1 implies negative number, 0 implies positive number. In given example, most significant bit is 1, therefore the number is negative number. Exponent is decided by the next 8 bits of the binary representation. 127 is the unique number for 32-bit floating point representation. It is known as bias. It is determined by 2 to the power k minus 1 minus 1, where k is the number of bits in exponent field. There are 3 exponent bits in 8-bit representation and 8 exponent bits in 32-bit representation. Thus, bias is equal to 3 for 8-bit conversion, which is determined by this formula, and bias is equal to 127 for 32-bit conversion. In given example, 0 is sign bit, next 8 bits are exponent bits, which are 1, 0, 0, 0, 0, 0, 1, 1, which represents 131 in decimal. Therefore, exponent will be 131 minus bias, that is 127, which is equal to 4. Hence, the exponent of the 2 will be 4, that is 2 to the power 4 is equal to 16. Mantissa is calculated from the remaining 23 bits of the binary representation. It consists of 1 and fractional part, which is determined by following example. 0 is sign bit, next 8 bits are exponent bits and remaining bits are mantissa. The fraction part of the mantissa is given by 1 into half plus 0 into 1 by 4 plus 1 into 1 by 8 plus 0 into 1 by 16 plus 0 into 1 by 32 plus 0 into 1 by 64 and so on, which is equal to 0.625. Thus the mantissa will be 1 plus 0.625, which is equal to 1.625. The decimal number is given as sign into exponent into mantissa, which will be equal to 26.
To convert a decimal into floating point, we have three elements in a 32-bit floating point representation. First sign, second exponent, and third one is mantissa. Sign bit. Sign bit is the first bit of the binary representation where 1 implies negative number and 0 implies positive number. Example, to convert minus 17 into 32-bit floating point representation, sign bit equals to 1. Exponent is decided by the nearest smaller or equal to 2 raised to the power n number. For 17, 16 is the nearest 2 raised to the power n. Hence, the exponent of 2 will be 4, since 2 raised to the power 4 equals to 16. 127 is the unique number for 32-bit floating point representation. It is known as bias. It is determined by 2 raised to the power k minus 1 minus 1, where k is the number of bits in exponent field. Thus, bias equals to 127 for 32-bit. Now, 127 plus 4 equals to 131, that is 1, 5 times 0, 1, 1 in binary representation. Now, let's move to the mantissa part. 17 in binary equals to 1, 3 times 0, 1. Move the binary point so that there is only one bit from the left. Adjust the exponent of 2 so that the value does not change. This is normalizing the number 1.001 into 2 to the power 4. Now consider the fractional part and represented as 23 bits by adding zeros, that we will get 0001 and 17 times 0.
So next slide is IEEE standard 754 floating point numbers. The IEEE standard for floating point arithmetic is a technical standard for floating point computation, which was established in 1985 by the Institute of Electrical and Electronics Engineers. The standard addressed many problems found in the diverse floating point implementations that made them difficult to use reliably and reduce their portability. IEEE standard 754 floating point is the most common representation today for real numbers. on computers including Intel-based PCs, Macs, and most unique platforms. There are several ways to represent floating point number, but IEEE 754 is the most efficient in most cases. IEEE 754 has three basic components.
The biased exponent. The exponent fields need to represent both positive and negative exponent. The bias is added to the actual exponent in order to get the stored exponent. The normalized mantissa. The mantissa is a part of a number in scientific notation or a floating point number consisting of its significant digits. Here we only have two digits, that is 0 and 1. So normalized mantissa is one of with only 1 to the left of the decimal. IEEE 754 numbers are divided into two biased on the above three components, single precision and double precision number. Now coming to the table, there are two types of single precision and double precision. Sign of single precision is 1 of 31st bit and double precision sign is 1 of 63rd bit. Biased exponent are 8, 30 minus 23 and 11 of 62 minus 52. Normalized mantissa of single precision is 23 of 22 minus 0 and double precision is 52 of 51 minus 0. Bias is 127 and the double precision bias is 1023.
Hello everyone, let's start with the example. We will convert 85.125 in single and double precision. 85 in binary is 1010101. 0.125 in binary is 001. Therefore, 85.125 in binary is 1010101.001. After normalization, we will get 1.01010101 into 2 to the power 6. As 85.125 is a positive number, sign bit is 0. First, we will convert it in single precision. Biased exponent will be 127 plus 6, which is 133. 133 in binary is 1000101. Normalized mantissa is 01010101. We will add zeros to complete the 23 bits. The IEEE 754 single precision is 0 as sign bit, 100000101 as exponent bits, and 0101010000 till 23 bits as mantissa. This can be written in hexadecimal form as 42AA4000. Now we will convert it in double precision. Bias exponent for double precision will be 1023 plus 6, which is equal to 1029. 1029 in binary is 10000000101. Normalized mantissa is same, that is 01010101. We will add zeros to complete the 52 bits. Therefore, the IEEE 754 double precision is 0 as sign bit, 10000000101 as exponent field, and 0101010000 till 52 bits as mantissa. This can be written in hexadecimal form as 405548 and 10 zeros. Exponent will depend upon bias, but mantissa will be same for both single precision and double precision. In single precision, we have to add zeros to complete 23 bits, and in double precision, we have to add zeros to complete 52 bits. Keep studying. Thank you.